Sometimes the methods by which science makes its discoveries are no less astonishing than the discoveries themselves. In the context of gamma-ray bursts, this statement takes on special significance, for their history is filled with unexpected turns. Among all the thrilling narratives they reveal, their origin is undoubtedly the most astonishing. This story begins, quite literally, in the midst of the Cold War and continues to this day, for true stories rarely have endings. Yet it is precisely this tale that has led humanity to understand the most colossal and violent events in the universe, paradoxically invisible to our eyes. After World War II, former allies, the United States and the Soviet Union, found themselves on opposite sides of an ideological divide. Their joint struggle against a common enemy gave way to a new, colder confrontation. The US and USSR became implacable rivals, each striving to outdo the other. Armed with nuclear weapons, both sides recognized the terrifying likelihood of mutual annihilation, and treated this threat with utmost seriousness. Both powers relentlessly tested nuclear weapons, steadily increasing their destructive potential. At the same time, they vigorously advanced space technologies, deploying satellites for mutual espionage. The idea even emerged of orbital platforms capable of launching nuclear strikes within mere minutes, far faster than the hours required for intercontinental ballistic missiles. Fears surrounding this threat led to the 1963 Partial Test Ban Treaty, which prohibited nuclear weapons testing and use beyond Earth's atmosphere. Both the Soviet Union and the United States became signatories to this pivotal agreement. Nevertheless, mutual distrust persisted. Fearing that the USSR might conduct secret tests, such as detonating nuclear warheads on the far side of the Moon, where detection would be difficult, the United States launched a series of satellites named Vela. Nuclear explosions produce gamma rays, the most energetic form of light, and the Vela satellites were specifically designed to detect this intense radiation. Two scientists, Ray Klebesadel and Roy Olsen, were tasked with analyzing the incoming data. They meticulously scrutinized every signal that might indicate a nuclear launch. For a long time, all signals proved false. But in 1969, they made their first significant discovery: a gamma-ray flash detected by multiple satellites on July 2, 1967. However, there was a catch: the source was not a nuclear explosion. The quantity of gamma rays and the pattern of their decay over time are distinctive signatures of nuclear weapons. The July 2 event looked entirely different. It featured a sharp, powerful burst lasting no more than a second, followed by a longer, but less intense emission stretching over several seconds. A quick check of solar flare data showed no solar activity that day capable of producing gamma rays. This was deeply puzzling. Over time, more mysterious gamma-ray bursts were detected. As analytical techniques improved, it became clear these rays did not originate from Earth's surface or near-Earth space. Regardless of their nature, the bursts came from random points on the celestial sphere and occurred in deep space. In 1973, Klebesadel and Olsen published their findings, sparking keen interest among astronomers. What could possibly cause gamma-ray bursts? Gamma-ray production is a complex process requiring extremely energetic events, such as stellar explosions, giant solar flares, or similar phenomena. Yet these bursts were linked to none of the known events. Moreover, gamma-ray bursts faded rapidly, lasting only seconds or minutes, making them nearly impossible to track with telescopes. Pinpointing their location in space took weeks or months after detection. Even then, significant uncertainties remained, as gamma-ray telescopes lack precision and cannot accurately determine direction. This situation was akin to someone dropping a coin and asking for help finding it, only to reply, when asked where it fell, somewhere in Wyoming. As more bursts were discovered, it became evident they occurred at random points across the sky, which itself posed a problem. If the bursts resulted for example, from comets colliding with neutron stars, a leading hypothesis at the time, we would expect to see more bursts along the plane of the Milky Way, where massive stars, and thus neutron stars, form. Yet bursts appeared uniformly across the entire sky. Observations of gamma-ray bursts, GRBs, led to a paradoxical conclusion. Either these immensely powerful cosmic events occurred very nearby, within a few hundred light-years, or they originated so far away that the influence of nearby galaxies on their distribution became negligible. For instance, scientists detected no excess of GRBs from the Virgo cluster, suggesting their sources lie in distant galaxies, in the farthest recesses of the universe. Yet neither explanation provided full clarity. Astronomers could not identify any nearby objects capable of producing such bursts, while the energy required to make a GRB visible across millions of light-years seemed unimaginably vast. Thus, gamma-ray bursts became one of astronomy's greatest mysteries for decades. The only hope of solving this enigma lay in faster response times, enough to catch the fading afterglow before it vanished. That hope became reality in 1997. A year earlier, the Italian-Dutch satellite BeppoSAX had been launched, designed to detect fleeting bursts of high-energy light and pinpoint their locations with unprecedented accuracy. In 1997, it detected a gamma-ray burst and provided a precise enough sky position for ground-based telescopes to confirm it within hours. For the first time, astronomers observed the fading afterglow of a GRB, and were stunned to find it originated above a faint galaxy. Several months later, another burst was detected in a different faint galaxy. When its distance was measured, astronomers were once again astounded. It lay 6 billion light-years away. The GRB mystery seemed solved, but instead gave way to an even grander puzzle. These explosions were occurring at colossal distances, meaning they must be unimaginably powerful. What could possibly unleash such an explosion? When it comes to immense power, black holes immediately come to mind. Black holes form when the cores of massive stars collapse and explode. Yet a problem remained. Even at such distances, the brightness of these bursts exceeded what a typical supernova could produce. The most energetic events known in the universe at the time couldn't explain GRB intensity unless. Astronomers proposed a bold hypothesis. What if the energy from a supernova was somehow focused? Normally, supernova energy radiates in all directions, expanding like a celestial sphere. But if that energy could be collimated into narrow beams, it might explain the observed flashes. We now understand that this is exactly what happens. When the core of a massive star collapses to form a black hole, infalling matter swirls into a hot, rotating vortex called an accretion disk. The magnetic field surrounding this material and the black hole gets twisted by the disk's rapid rotation, channeling energy upward and away from the black hole. Though details remain unclear, this process launches jets of matter and energy outward at nearly the speed of light, punching through the star and erupting into space. The energy in these jets is staggering, equivalent to an entire supernova. These death rays are so luminous we can detect them billions of light-years away. The supernova producing such jets isn't ordinary, it releases far more energy than a typical supernova. Astronomers dubbed these events hypernovae. It's a truly awe-inspiring phenomenon. And remarkably, no special equipment is needed to witness one. On March 19, 2008, a bright gamma-ray burst occurred 7.5 billion light-years from Earth. Despite that immense distance, it flared so brightly that anyone looking at that patch of sky would have seen it with the naked eye. Some scientists believe the jet was pointed directly at us, hence its brilliance. Fortunately, it was extremely distant. This explains gamma-ray bursts, or at least one type of them. In fact, there are two distinct classes. Careful analysis of burst durations reveals two groups: long bursts lasting more than 2 seconds, caused by hypernovae, and short bursts, some as brief as 1/1000th of a second. These are too rapid to result from core collapse in supernovae, so another cause must exist. What else could unleash energy rivaling a hypernova? The answer: the collision and merger of two neutron stars. Imagine two massive stars born together in a binary system. One explodes as a supernova, followed by its companion, leaving two neutron stars orbiting each other. They might remain in this state forever, were it not for gravity, as predicted by Einstein's theory of relativity. Massive orbiting objects slowly lose orbital energy by emitting gravitational waves, ripples in spacetime. Though this may seem exotic, it effectively causes their orbits to shrink. Over billions of years, the two neutron stars inch closer together, their orbital speed increasing as they approach. Eventually, they merge in an instant. If their combined mass exceeds 2.8 solar masses, they collapse into a black hole. What follows is extraordinary. For a brief moment, the system becomes a black hole surrounded by dense debris from the merger, material rich in neutronium, the substance of neutron stars. This debris forms an accretion disk, heats to extreme temperatures, and launches jets of matter and energy, mimicking the hypernova process. Because the material is so dense, the resulting gamma-ray flash is much shorter. If you've ever wondered what the stuff of cosmic nightmares looks like, this is it. This brings us to the in-focus question: if gamma-ray bursts are so powerful we can see them from halfway across the universe, what would happen if one occurred nearby? The consequences would be catastrophic. The dangers of a nearby supernova are well known, and GRBs pose comparable threats. But because GRB energy is beamed, the danger persists regardless of distance, whereas a supernova must be within a few hundred light-years to harm us. A GRB could be as far as 7,000 light-years away, and still inflict similar damage. Fortunately, these beams are extremely narrow, so we only see a burst if it's pointed directly at Earth, greatly reducing the chance we'd be hit by a nearby one. Two stars within the danger zone could potentially produce GRBs, Eta Carinii and WR104. The good news is both lie near the edge of the hazardous distance, making significant harm unlikely. Even better, current data suggest their jets aren't aimed at Earth. Moreover, no hypernova progenitors currently threaten us, and no neutron star binaries are known to be on the verge of merging. Such systems are rare and likely distant, so there's no cause for alarm. In recent years, numerous observatories have been built specifically to detect bursts. One of the most important is NASA's Swift Observatory, designed to identify GRBs from any explosion and swiftly pivot its ultraviolet telescopes to pinpoint the location. Coordinates are then relayed to Earth, enabling ground-based telescopes to join the observations. By 2015, Swift had detected over 900 gamma-ray bursts. Rapid response is crucial for capturing burst data, and since Swift's launch, our understanding of these phenomena has dramatically improved. Today, with a fleet of satellites scanning the sky, we detect a gamma-ray burst nearly every day. But remember, we only see them when their beams point at us. That means most go unnoticed, and the true rate of GRBs in the universe is far higher. Hundreds may occur daily, scattered across the cosmos, silent, invisible, and unimaginably violent, yet revealing the universe's most extreme physics. Gamma-ray bursts are among the most astonishing events in the universe. They are the most violent and energetic explosions the cosmos can produce. Everything about them is remarkable, from their discovery to the source of their immense power, and what they ultimately become. In fact, perhaps the most astonishing thing about them is this: every time we observe one of these explosions, we are witnessing the birth of a black hole. Gamma-ray bursts are the birth of black holes. It's now known that gamma-ray bursts were first detected during the Cold War, when the United States and the Soviet Union were monitoring space for signs of clandestine nuclear weapons tests. These bursts come in two varieties, long and short. Long bursts originate from hypernovae, massive stars that explode, ejecting two powerful jets of energy and matter. Short bursts result from the merger of neutron stars. Both types release staggering amounts of energy and can be detected across distances of billions of light-years. And both herald the formation of a black hole. Crash Course is produced in partnership with PBS Digital Studios. Visit their YouTube channel to watch more incredible videos. This episode was written by Phil Platt, edited by Blake DeBastian, and Dr. Michelle Tholler served as scientific consultant. Directed by Nicholas Jenkins, edited by Nicole Sweeney, and sound design by Michael Aranda. Graphics by Thought Cafe.